Alright, thanks for coming. So today is Duksang Lee. We talk about graphic delta-matroids. Section is over this. Intersection with the matroid. Please.
Okay, thanks for coming and thanks for introducing. This talk is about characterizing matroid, whose base form are kinds of combinatorial object which is called graphic delta-matroid. This talk is based on joint work with Professor Sang-il Oum. This talk consists of 3 parts. In the first part, I give a definition of graphic delta-matroid, delta graphic matroid, and graphic delta-matroid, and why delta graphic matroid comes up. And in the second part, I introduce some main results about characterizing delta graphic matroid. The first result is about decomposition theorem, and second one is about excluded minors. And in the last part, I'll give a sketch of proof of some results. So let me start with introducing some motivating combinatorial object. First one is matroid. I'll give 2 examples of matroid. First example come from graph. For a simple argument, we may assume that G is connected and consider the collection of the edge set of spanning tree. Then we know that we form a matroid, and this matroid is called to a cycle matroid of G. Also, matroid M is a matroid is called graphic if it is isomorphic to some cycle matroid for some graph G. The second example comes from matrix. Let A be a matrix defined over a field F. Then we consider the collection of the subset of column vectors which form a basis of column vector space. Then this collection also forms a matroid which is called linear matroid over matrix A. Then 2 collections which define a matroid satisfy the following property. Whatever we choose to set B1, B2 in the collection and given any element X in B1 delta B2, which means the symmetric difference of B1 and B2. And we can choose an element Y in B1 delta B2 such that the B1 symmetric difference with B1 and the set XY is again contained in B. And we say that this property is a symmetric exchange axiom. So the second example comes from symmetric matrix or skew symmetric matrix. Let A be a skew symmetric or symmetric V by V matrix defined over a field F. Then now let me define F of A as a collection of the subset X of V such that X satisfies either X is empty set or the principal submatrix of A induced by the set X is non-singular, which means determinant is non-zero. Then Boucher also proved that the F of A satisfies the symmetric exchange axiom. The third example comes from graph. A graph is a pair of a graph G and a subset T of VG. And the graph looks like this. You can visualize like this. And we may assume that each component of G has at least one of T for a simple argument. And now we define a specific kind of subgraph, which is called T-spanning subgraph. A subgraph H is a T-spanning subgraph of graph GT if the whole vertex set of H is equal to VG and for each component contains the odd number of vertices of T. Here is an example. The purple subgraph is a T-spanning subgraph over graph GT because each component contains an odd number of vertices of T. So Sang-il proved that when you consider the FGT as a collection of edge set of T-spanning forest, then it also satisfies the symmetric exchange axiom. As a side remark, when you consider the case G is connected and T has a size 1, then we know that the T-spanning forest is just a spanning tree of G. So in this case, FGT is exactly the same as the collection of the edge set of spanning tree of G, which form a cyclomatroid over graph G. So there are many combinatorial objects satisfying the symmetric exchange axiom. So it seems to be natural to come up with some abstract object with this property. So Boucher defined the delta-matroid. E is a binary set and F is a non-empty collection of the subset of E. Then a pair of E and F is a delta-matroid if we satisfy this symmetric exchange axiom. Also, we say that an element of F is a feasible set of M. And in particular, a delta-matroid, if a delta-matroid M is a matroid, then we call an element to base of a matroid M. Now let me define some operation over a delta-matroid. Let M be a delta-matroid defined over a set V and X be a subset of V. Then let F delta X is a collection of the set which is obtained from each feasible set over F M by taking symmetric difference with X. Then together with V, this collection form a delta-matroid, and we denote it by M delta X. Then we say that M delta X is a delta-matroid obtained from M by twisting X. Also let M be delta-matroid. Then we say that N is a minor of M if N can be obtained from M by taking twisting operation and deletion operation. So here is an example of delta-matroid. First example comes from matroid. We say that a delta-matroid N is twisted matroid if N is equal to some matroid up to twisting operation. So the second example is come from skew-symmetric matrix. Given a V by V skew-symmetric or symmetric matrix A defined over a field F, then we already observed that M of A is a delta-matroid because F of A satisfies the symmetric exchange axiom. So we say that a delta-matroid M is F representable delta-matroid if M is equal to M of A up to twisting for some symmetric or skew-symmetric matrix defined over a field F. The last example comes from graph. We also know that GGT is a delta-matroid, even it is a binary delta-matroid. Then we say that M is graphic if M is equal to GGT up to taking twisting for some graph GT.
So regardless, so you could say a twisted matroid is a matroid twisted with any set?
Yeah, yes.
Okay. So it doesn't need to be a base.
Actually, there is another definition with base, twisting with base, right? But yeah, now I'm gonna define the twisted matroid like this. Also, we know that this kind of delta-matroid is defined by some specific combinatorial structure by taking twisting, because it is for the class of this delta-matroid to be minor close. So now we focus on third example, graphic delta-matroid. So we want to get a characterization for the class of graphic delta-matroid. But about this problem, there are many open problems. So now we consider the graphic delta-matroid, which are also twisted matroid. So we define delta graphic matroid. A matroid M is delta graphic if there is a graph GT such that M is equal to GGT up to taking twisting operation. So by this definition, we can check that the class of twisted delta graphic matroid, which means the closure of the class of delta graphic matroid with symmetric twisting operation, is exactly the same as the intersection class of intersection class of graphic delta-matroid and binary twisted matroid. This is also come from the graphic delta-matroid is a binary. So we already observed that the cycle matroid is a special case of graphic delta-matroid. So the twisted graphic matroid is a subclass of twisted delta graphic matroid. Also, twisted graphic matroid contain the class of graphic matroid and the class of cographic matroid. Cographic matroid is a dual of graphic matroid. So we want to characterize the class of delta graphic matroid. And about this problem, we got two results. First one is the decomposition theorem. This theorem gives how can we construct the delta graphic matroid. And second theorem gives a bound size of excluded minor. Actually, by the well-quasi-order theorem for binary matroid due to Villan-Girard-Whittle, we already know that there are finitely many excluded minor. So we also know that there are some numbers such that the excluded minor have bounded size. But we don't know any explicit value, so this theorem does not imply our result. So now I want to talk about decomposition theorem. But before I do that, let me give one more definition to some of matroid. Let M1, M2 be matroid such that M1 is defined on set E1 and M2 is defined on set E2, such that E1 and E2 intersect with single element set. Then we define the two sum of matroid M1, M2 by a matroid defined on set E1 delta E2, whose base form looks like this. But I'm gonna explain with some example. Let M1 be a cycle matroid of both cycle and M2 be a cycle matroid of triangle. Then both matroids share a common edge, E. Then we choose base B1 from M1 and B2, or base B2 from M2, such that the chosen base B1, B2 should satisfy the condition. The condition is one of B1, B2. If one contains E, then the other should not contain E. in this case, B1 contains E and B2 does not contain E. Then after we choose two bases with this condition that we construct the two-sum of matroid, the base of two-sum matroid by taking disjoint union and deleting E. So this is how can you construct the base of two-sum matroid. So this is our first theorem. A connected matroid M is delta-graphic if and only if M is obtained from the cycle matroid of a minor of Hill graph by gluing graphic matroid along limb edges, which is blue edges, with two-sum operation, and cographic matroid along spoke edges with two-sum operation. This gives a two corollary. A first corollary say that every delta-graphic matroid is regular. A regular matroid is a matroid which is representable over every field. And this corollary comes from the fact that graphic matroid and cographic matroid is regular, and two-sum of two regular matroid is also regular. So the second corollary say that a three-connected matroid M is delta-graphic if and only if M is just graphic or cographic matroid. This is because three-connected matroid cannot decompose into small two matroid with two-sum matroid, two-sum operation. So this is our second theorem about excluded minor characterization. If M is a matroid which is minor minimally not delta-graphic, then it has a size at most 48. So in the remaining of this talk, I'll give a sketch of proof of some result. Before I sketch the proof, let me mention the graphed minor. There are two operations for graphed. First one is deletion, and the other one is contraction. Deletion operation is not different with the deletion operation for graph. However, contraction is a little bit different. This is because the resulting vertex may not be in T or maybe in T. So when we do the contraction for graph say that when you contract an edge, the resulting vertex is in T if only one of end vertex of edge what I contract is in T and the other is not in T. Then we know that the graphic delta-matroid which come from minor of a graph GT is a delta-matroid minor of graphic delta-matroid which come from a original graph GT. So what we first have to do is finding graph GT, satisfying that GGT is a twisted matroid. For this, we use a theorem due to Duchamp, characterizing the excluded minor for the class of twisted matroid. This theorem says that a delta-matroid M is twisted matroid if and only if it has no minor isomorphic one of two matroid, D1 and MK3. However, we don't have to consider about this because actually it is a forbidden minor for the class of even delta-matroid. Even delta-matroid is a delta-matroid whose all visible sets have the same parity. And Sang-il also proved that graphic delta-matroid is already even. So this minor already forbidden, so we only need to care about MK3.
So in the step one, you want to find the graph to satisfy the GGT is not a twisted nature. Maybe.
Yeah, so I want to forbid some obstruction. I want to find the obstruction and forbid here. So the problem is same as finding graph such that GGT which has no minor isomorphic to MK3. Actually up to taking twisting operation. So we can find that this Deltamatroid has a graphic Deltamatroid which is isomorphic to MK3 up to taking twisting operation. So the problem is, this problem is same as finding graph GT which has no graph to minor isomorphic to one of these three graphs. So what such a graph looks like? Roughly speaking, we proved that those graphs looks like this. The left one is come from even cycle. I will say this kind of graph to a graph with even cycle decomposition, and this is the graph with past decomposition. And we proved that the graphic Deltamatroid which come from this graph is a matroid which is obtained from a cycle matroid of hill graph by gluing graphic matroid and cographic matroid. And also this graph is always a minor of some even cycle decomposition graph too. So because we can delete other thing and we can make a path-like structure. So together with this fact, we can conclude that those kinds of graph make a graphic Deltamatroid which is obtained from a cycle matroid over a minor over hill graph by gluing graphic matroid and cographic matroid. So actually, in this way, we prove the decomposition theorem. But I'm not going to talk with more detail because of the time limit, and I focus on the proof of excluded minor theorem. So for excluded minor theorem, actually three-connected case is easier because we already know this corollary. The three-connected matroid is delta graphic if and only it's just graphic or cographic. So here is a lemma characterizing the three-connected excluded minor for delta graphic matroid. A three-connected matroid is delta graphic if and only it has no minor isomorphic to one of these five matroid. U24 and Bound matroid and dual Bound matroid and R10 and R12. Actually, we can easily check that this matroid is three-connected and is neither graphic nor cographic. So you can say that it is not delta graphic. So the forward direction is easily hold. And for the backward direction, we use a two theorem due to Todd and Seymour. Todd theorem gives a excluded minor characterization for the regular matroid. And Seymour theorem say that a three-connected regular matroid is a graphic or cographic or has a minor isomorphic to one of R10, R12. So suppose that we have a minor matroid M which has no minor isomorphic to one of these five matroid. Then since it was also forbidden, we can say that it is a regular. So by using Seymour's theorem, it is a three-connected regular metroid which has no minor isomorphic to 1 over R10 R12. We can say that it is a graphic or cographic. So by corollary, we can prove the backward direction of lemma. So we can finish to characterize the three connected excluded minor, and it is enough to consider the excluded minor which is not three connected. So for that, we use a tree decomposition for a metroid, which is good for looking at all two separation of metroid. So now let me define what tree decomposition is. Given a connected metroid M, we first start with metroid labeled tree. Metroid labeled tree is a tree such that each vertex corresponds to some metroid, such that two vertices are adjacent if two corresponding metroids share common element, and two vertices are not adjacent if two corresponding metroids define the disjoint set.
So you mean that each edge corresponds to separation?
Yes. Yeah, I'll talk later. Yeah, actually, this edge represents two separation for metroid. And also the common element of those metroid should not be loop and co-loop for those metroid, for both metroid. So we can define a contraction operation for metroid labeled tree. When you contract an edge, or let's contract the edge B, then the metroid corresponds to two end vertex is M2 and M3. Then after contracting B, then the resulting vertex corresponds to two sum of M2 and M3. This defines a contraction for metroid labeled tree, and we say that tree decomposition of metroid M is a metroid labeled tree such that when you contract all of edge and make a single vertex, then this single vertex should be correspond to the whole metroid M. So eventually we can see that this edges gives a correspond to two separation for metroid. So now let me give a special kind of tree decomposition which is called canonical tree decomposition. Canonical tree decomposition is a tree decomposition with two more conditions. First one is corresponding metroid is either three connected or uniform metroid of rank 1 or uniform metroid of rank 1. Actually, we can see the uniform metroid of rank 1 as a cycle metroid of this graph with two vertices and parallel edges, and we can see the uniform metroid of rank 1 as a cycle metroid over just the cycle. Also, the second condition is there are no adjacent pair of vertices such that two corresponding metroid are both uniform metroid of rank 1 and both uniform metroid of rank 1. we call such pair a bad pair. Then Cunningham and Edmonds proved that if M is connected, we can always find a canonical tree decomposition, and it is unique up to relabeling some edges. So, what is the canonical tree decomposition for delta-matroid metroid? Before we talk about it, let white vertex correspond to metroid, which is graphic and cographic, and blue vertex is a metroid for metroid, which is graphic and not cographic, and red vertex correspond to metroid, which is not graphic but cographic. Then by decomposition theorem, we know that the delta graphic metroid is obtained from the cycle metroid of a minor of hill graph. Then the first case comes when the minor of hill graph, what it start with to construct the delta-matroid, is a small metroid, small graph. The minor of hill graph has a small size. Then we eventually prove in this case, the structure of delta graphic metroid is just a twosome of a graphic metroid and a cographic metroid. So in the tree decomposition, we find the edge which is separating into graphic part and cographic part. So the tree decomposition structure roughly looks like this. However, it may not be canonical because it may be bad pair, which means both are uniform metroid of rank 1 or both are uniform metroid of rank 1. So to make it canonical, we contract this edge, and the result decomposition looks like this. So in this case, we get two kinds of tree decomposition. Also for second case comes when the minor of hill graph, what it start with, is just a hill graph. Then we know that the hill graph with large size, not very small size, is still connected. So the hill metroid is also still connected in terms of metroid connectivity. So the hill metroid comes up in tree decomposition structure, canonical tree decomposition structure. So we can find the vertex V, which corresponds to this metroid, such that when we delete V, each component should be correspond to graphic metroid or cographic metroid. Also, if the component correspond to graphic metroid, then these connecting edges should be limb edges, and this if the component is correspond to cographic metroid, then this connecting edge should be spoke edges. Also, the last case is when the minor of hill graph, what I start with, is a proper minor of hill graph, but the size is not small. Then actually most of proper minor of hill graph looks like the band graph. So in this case, we should come up with the cycle metroid of band graph, but band graph is not serially connected. It's not serially connected, and actually it can be decomposed by alternating to some of uniform metroid of rank 1, rank 1, rank 1, rank 1, so on. So we can find such path structure in tree decomposition. So we got a tree decomposition like this. So this kind of, we call this kind of tree decomposition structure or tree decomposition, and this kind of tree decomposition or band decomposition. So also, let me introduce some reduction rule of canonical tree decomposition. First reduction say that given a tree decomposition, canonical tree decomposition, and given a subtree of this tree, then the tree decomposition induced by this subtree is a canonical decomposition of a minor over matroid, which is isomorphic to a minor over original matroid. Also, the second reduction say that in tree decomposition, when we can find the path, induced path of length at least 2, then we can contract the path to edge or vertex, depending on whenever these two vertices are become bad pair eventually or not. So the resulting canonical tree decomposition is gives a matroid which is isomorphic to a minor of original matroid. So in this talk, I say the second reduction path contraction. So let M be a matroid which is minor minimally not delta-graphic, and tree decomposition tree decomposition is a given. And here is some observation about this matroid. First one is we can assume that every bag is a graphic or cographic, because if not, which means if there is a bag such that the corresponding matroid neither graphic nor cographic, then it should be three connected, because uniform matroid over length 1 and corank 1 is a cycle matroid or planar graph, so both graphic and cographic. So we can eventually get a three connecting excluded minor. So in this case, we can reduce the case to the case what already know. So we can assume that every bag is graphic or cographic. And second observation say that for every leaf vertex, the corresponding matroid cannot be planar matroid. Suppose that, which means we can find the leaf vertex V which correspond to graphic and cographic matroid. Then when we delete V, since M is minor minimally not delta graphic, then M delete V is a delta graphic. So you can get a tree decomposition like this, as I said before. So when you recover M, actually the tree decomposition structure is preserved. So in this case, we can conclude that M is delta graphic, which is a contradiction. So this gives a proof of the second observation. And now I give some key idea. There are three key idea what I want to say. And first one is called bang reduction. Actually, we only need to care about whether each bag is a graphic or not, cographic or not. So what I want to do is, if there is a bag with large size, then we want to reduce this corresponding matroid to its minor, so that the reduction, which means deletion, matroid deletion and matroid contraction, does not change the tree decomposition structure. Also, the color of this reduced bag. Then we can conclude that the reduced whole matroid is not delta-graphic, which is contradiction for the condition of M, minor minimally not delta-graphic. So this contradiction say that each bag cannot be large size, cannot have large size. So for this, we use a lemma due to Bixby and Collard. When you have a three connected matroid M and three connected minor of N and N of M, then also let E be an element which is not in N. Then there is we can find the three connected minor M prime of M such that M prime contains E and M prime contains also N as a minor. Also the size is still small. I explain more with more detail how we can use this lemma. Actually, for uniform matroid, this step is easier. So we now focus on the blue vertex or red vertex. We may assume that it is a blue bag such that the corresponding matroid has a large size. Then, since it is a blue bag, this matroid is not cographic but graphic. So we can apply the Kuratowski theorem for a matroid, and we can say that it has no minor. We can find the minor isomorphic to cyclomatroid of K33 and cyclomatroid of K5. So we can find such minor like this. If this minor contains an element which is correspond to this edge, this element and this element correspond to this edge in the tree. If this minor contains all of this element, then reduction operation does not change the tree decomposition. However, it may not be. So if this minor does not contain this kind of element, then deletion operation and contraction operation, after the deletion operation and contraction operation, the tree decomposition can be broken as a result. So I don't want to this situation. So by using this lemma, we want to extend from this matroid more and more, so that the extended matroid contain all of these elements correspond to the edge of tree. So you can do like this. So this is the rough idea what I want to do about bag reduction. And second idea is subtree reduction. Suppose that there is an edge E and the component as a result of deleting E, which is graphic, which correspond to graphic matroid and cographic matroid, then we can say that it originally should be a single vertex. Suppose not, then without loss of generality, we can assume that this part is a cographic part. Then we know that leaf cannot be both graphic and cographic, so we can find the leaf colored with red. So we restrict to subtree by first reduction, what I said, and next we apply the path contraction, so we get a kind of this structure. However, we already assume that M is not equal to this subtree is not a single vertex, so this minor is actually a proper minor of M. So by the condition of M, which is minor minimally not delta-graphic, we can say that this 3D composition gives a matroid which is delta-graphic. So we get a 3D composition structure like this. And similarly, when you recover this, the 3D composition structure does not change. So we can conclude that M is delta-graphic. So this gives a contradiction. So last key idea is excluding some substructure described in terms of 3D composition. Let's consider this kind of 3D composition structure with path of length 2 and each back colored with red, or blue, red, blue. Then we can observe that it is not delta-graphic because it has no field matroid or path of uniform matroid. So this 3D composition cannot be field decomposition or band decomposition. So if it is a delta-graphic, it should be just a two-sum of a graphic matroid and cographic matroid, which means that we should find an edge separating into graphic part and cographic part. However, it is impossible. So we can say that it is not delta-graphic. So suppose that M has this structure as a minor, then since it is a minor minimally not delta-graphic, if it contains this structure as a proper minor, then it is a contradiction for the condition of M. So actually M should be isomorphic this one. So by using band reduction, what I said before, we can prove that each bag should have a small size, and we can conclude that M, in this case, M should have the small size. So next, we can assume that M has no minor, M has no such a structure. Then, in the 3D composition of M, we can say that there is no path between two red vertex such that at least one of internal vertex is a blue vertex. Similarly, the path between blue vertex such that at least one of internal vertex is red vertex. If we can find such a structure in the 3D composition of M, then by taking a path decomposition, path contraction operation, we can find this structure. So it is a contradiction. So now eventually we can prove that forbidding this structure, we can prove that M has a canonical tree decomposition such that every internal vertex should be planar, should be correspond to planar matroid. So this step reduce the 3D component structure more simple. So we recursively apply this step, similar step for more obstruction, H prime matroid, H matroid, MK event. Actually, there is a condition given for each bag to this matroid to be not delta-graphic. Yeah, so yeah, eventually it is a obstruction of for the delta-graphic 3D composition structure. So this is the, using 3 key ideas, we can prove the excluded minor characterization. So now let me finish with introducing some open problem. First one is about characterizing the intersection class of graphic delta-matroid and regular delta-matroid. Also, I wonder what is the characterization for the intersection class of graphic delta-matroid and Eulerian delta-matroid. Actually, Eulerian delta-matroid is characterized with circle graph, and it is a subclass of regular delta-matroid. So one is harder than 2. So for the third question, we can see a graph as a vertex group labeled graph when group is G2. So I wonder, can we define delta-matroid which come from vertex group labeled graph for more complicated group? For example, general cyclic group. But I don't know whether it is easy or not. I don't know about this problem. So this is the end of my talk. Thank you very much.
Thank you. Any questions?
Biggest obstruction? I think one of the biggest obstruction looks like this, because actually the white vertex corresponds to very small bag, and the colored vertex corresponds to relatively large bag because it contains this kind of obstruction. So the size already big. So there are one more characterization, what I didn't mention in this talk, a kind of the trees looks like K4, and this is the planar matroid, and the two of them are red vertex colored with red, and two of them colored with blue. But it is not isomorphic to pure matroid. So since it is not pure matroid, we cannot say that it is a delta-graphic, but actually we don't know, we don't find the specific structure of this bag of the structure in this case. Just the bound of size in this spec.
Yeah, but anyway, can you give any explicit example of orbital minor?
Explicit.
Like
one
something
of
that
these.
can uses. Maybe that's Jungwon's question.
I want to see a linear gap between the upper bound and the structural bound.
Any orbital minor, then you know.
Right, this? Actually, this metric come from this structure.
Other questions? If there's no further questions, let's thank the speaker again. Next thing is definitely.